So, when you hear the word norms, you're probably picturing societal rules, right? Like shaking hands when you meet someone or saying please and thank you. But today, we're looking at something entirely different. We aren't talking about social etiquette at all. Instead, we're diving into the hidden mathematical laws that are literally shaping the 21st century's digital landscape. Welcome to this explainer on the role of norms today. Okay, let's dive into this. What invisible mathematical rules actually govern today's algorithms? I know, it sounds a bit like a philosophical question, but it's incredibly practical. We're going to kick off a really fascinating journey today, and it's going to take us all the way from a few seemingly abstract algebraic equations straight to the very real recommendation engines that tell us what to watch, buy, and read every single day. Here is our roadmap for the explainer. We'll start by defining mathematical norms, then compare L1 versus L2 geometry. After that, we'll look at regularization in machine learning, navigate through high-dimensional data, and wrap up with how all of this powers modern recommender systems. All right, jumping right into section 1, defining mathematical norms, measuring the abstract. Let's demystify this word norm right off the bat. In math, and specifically linear algebra, the norm of a vector is simply a non-negative number that describes its magnitude, or its length, in space. If you just think of a vector as an arrow pointing somewhere on a graph, the norm is literally just a way to calculate exactly how long that arrow is. Pretty straightforward, right? So, how do we actually calculate that length? Well, we've got two main competing mathematical philosophies here. On one side, we have the L1 norm. You'll also hear this called the taxicab or Manhattan distance. It just takes the sum of the absolute values of a vector's components. Think about driving in a grid-like city. You can't go through buildings, so you have to drive down the blocks and take right angles, usually while stuck behind a garbage truck. On the flip side, we have the L2 norm, or Euclidean distance. This one calculates the square root of the sum of the squares. Basically, it's the as the crow flies straight line distance from point A to point B. Oh, and there's also a third kind of specialized way to measure this called the infinity norm or max norm. Instead of summing everything up, this norm just returns the single maximum absolute value of a vector's components. You can think of it as acting almost like a filter. It isolates only the single largest dimension in a data set and completely ignores all the smaller values. Moving right along to section 2, L1 versus L2 geometry, the diamond and the circle. If you plot the L1 norm out on a graph as a constraint, it forms this really distinct diamond shape. Try to picture this diamond in your head. It has very sharp, distinct corners that lie perfectly on the axes of the graph. When a machine learning algorithm is trying to minimize its error while being constrained by this diamond, the optimization path naturally hits those sharp corners. And because those corners sit exactly on the axes, it forces the machine learning weights of less important features to drop to exactly 0. In data science, we call this creating sparsity. Now contrast that sharp L1 diamond with the smooth circle constraint of the L2 norm. A circle totally lacks those sharp corners. So when the algorithm tries to minimize its error here, the loss function ellipses touch the circular constraint smoothly at almost any point. The result? The weights shrink evenly, but they rarely hit absolute 0. They just get super, super small. Which brings us to section 3, regularization in machine learning, keeping models honest. Let's put this into perspective with some actual numbers. When we run simulations of random loss functions, the L1 regularization, that sharp diamond, pushes an incredible 66 to 72% of coefficients to exactly 0. Compare that to the smooth L2 circle, which only zeroes out a tiny 3 to 5% of coefficients. That is a massive behavioral difference, and it's driven entirely by geometry. Practically speaking, L1 is highly valued for feature selection because it basically acts as a ruthless editor. If a feature is useless, L1 assigns it a 0 and just throws it out. But L2? L2 handles codependent or collinear features beautifully. If your dataset tracks, say, gender and is pregnant, L2 shrinks them evenly to keep the model stable rather than just arbitrarily zeroing one out. All right, section 4, navigating high-dimensional data, the curse of dimensionality. So remember how the L2 norm is calculated by taking the square root of the sum of the squares? Well, in high-dimensional space, that squaring term becomes a huge liability. When massive, extreme outliers randomly pop up in a huge dataset, squaring those extreme deviations completely overwhelms the calculation. It unfairly punishes the model, dragging the whole thing off course just to accommodate a few bizarre data points. But check out this fantastic quote regarding the L1 norm. The Manhattan distance will sort of shrug it off because it's more influenced by the closeness of the other variables. Because L1 doesn't square the errors, it acts as this incredibly robust shield. It's vastly superior for high-dimensional data because it literally just ignores those extreme, bizarre outliers and focuses on the underlying truth of the dataset. And finally, we arrive at section 5. Powering modern recommender systems, the L3F model. Recommender systems like the ones humming away at Amazon or Netflix deal with what's called high-dimensional and sparse, or HIDS data. Think about it. A single user can't possibly interact with every single item on Amazon. It's impossible. This creates these massive user item matrices filled with giant gaps of missing entries. The algorithm, which is usually a latent factor model, has to look at the few things you actually did rate and then predict the millions of things you didn't. But here's the real-world problem we run into: the threat of outliers. In literally any open system, you're going to have malicious users or bots assigning extremely high or low fake ratings to items just to skew the system. And if an algorithm relies purely on the L2 norm to make its predictions, remember what happens. Those extreme fake ratings get squared and they easily derail the prediction model. And this brilliantly illustrates exactly what we're talking about. Over on the left, you see some data points, but notice those couple of massive outliers sitting way up high? Check out the solid green line representing the L2 norm. It gets dragged violently upward, totally skewed by those fake ratings. But then look at the dashed pink line of the L1 norm. It essentially just ignores the outliers and stays true to the real trend. However, if you look at the right side, you'll see L2 actually provides a much smoother curve when predictions are close to the truth. It gives a stability that the sharp L1 shape kind of lacks. So researchers looked at this and asked, well, why not use both? And that led to the cutting-edge L3F model, an L1 and L2 norm-oriented latent factor model. It is the ultimate compromise, really. It dynamically aggregates both norms during training. It adaptively increases the weight of the L1 norm when it detects outliers to shield the system, and relies on the L2 norm to keep predictions incredibly smooth and accurate otherwise. By combining L1's robust outlier resistance with L2's smooth stability, it just brilliantly conquers missing data in high-dimensional matrices. Which brings us to the end of our explainer, and it leaves us with a pretty profound question. We just saw how choosing between a simple sum or a squared calculation drastically changes what a machine learning model actually cares about. It decides whether an outlier is just brushed off or whether it derails the whole system. So if mathematical norms quietly govern our algorithms, who governs the norms? The choices made by data scientists in selecting these abstract shapes define the role of norms today, ultimately shaping our daily digital reality. Definitely something to ponder the next time you get a perfectly timed recommendation.